we have the diagram on the left which shows the three different states of matter, the solid, the liquid, and the gas. On the left hand side we have shown the temperature. So you have, like, if you increase the temperature, there's more kinetic energy. You have more kinetic energies. The gases have more kinetic energies than the liquids. Liquids have more kinetic energies than the solids. And this is represented by the temperature, right? The temperature is the average kinetic energy of the system, right? Okay, so very simple concepts. You guys already know this. Just for the completion of this whole, the understanding, I'm just iterating it. When you move from solid to liquid by increasing the temperature, it's called melting. The reverse process is called freezing. When you have a liquid, when liquid moves to gas, it's called evaporation or vaporization. We'll quickly discuss about evaporation and boiling when I just finish this. There's a subtle difference between them. It's very important to understand. And the reverse process from the gaseous to the liquid is condensation. Now, interestingly, solids can directly change to the gaseous state. All right. So the direct change of solid to gas is called sublimation. The reverse process is called condensation in here. Okay, you remember like how we call this the condensed phase? So condensation from gas leading to the condensed phase liquid or the condensed phase solid. Okay, now what's the difference between evaporation and vaporization? So vaporization is also called boiling. Evaporation happens at any temperature. So like for example, if you spill some water in here, come back a little later, it might have evaporated, right? Why? Did the temperature go to 100 degrees Celsius? No, but there was a phase shift. How did it happen? It was evaporation, right? So at a fixed temperature, when there was a boiling or vaporization, as you saw in the heat versus the temperature diagram, that was not evaporation, that was boiling, because that was happening at the boiling point, at a fixed temperature. Evaporation happens at any temperature, while boiling or vaporization is at a fixed temperature, and which is the boiling point. Now, another important thing to understand here is all these processes that we are seeing, all these phase changes, are also dependent on pressure. In here, for our understanding, for our basic understanding, we'll assume that all these things are happening at a constant pressure, and pressure is not playing a role in these processes. But in reality, if you change the pressure, the temperature of all these different processes will also change. So the temperature and pressure both play an important role in determining the states of the matter and what phase water or per se for any matter per se will exist. For now, we are considering pressure as constant, but you have to keep in mind that pressure determines temperature. Okay? No, sorry. Pressure and temperature both determine the phases, the states of matter. Okay? All right. So there is another concept called evaporation, which is really interesting, and for that we'll bring back the concept of this bell curve, in which we have the distribution of the particles. Say we have the distribution at 50 degrees Celsius for a closed system like this. Okay, so we have liquid water, something like this. The balls in here represent the particles in the liquid. So for example, we have this liquid in a container like this. This is an open system, it's not covered, but let's assume that this is a closed system in here. Okay, so there is this liquid layer which demarcates the boundary between the liquid phase and the gaseous phase, right? And all these have an average temperature of average kinetic energy, which is determined by, which is shown by this temperature, right? This, if I measure this, this will give me a temperature. Let's assume this is 50 degrees. So this is the average kinetic temperature. But we have to understand that not all the particles will have the same kinetic energy. Why? Because like in a test, the average score of the class, say, was 75. But that doesn't mean that every student in the class got a 75. Someone would have got less marks, like 50, 40, and things like that. And some students might have got like higher, like 70, 80, 90, 95, whatever. So these are, the same goes for these water molecules. there will be some particles which will be highly energetic. Now what happens to those highly energetic particles? Will they want to stay in the liquid state? No, they don't. They don't want to remain in this liquid state. What they want to do? They want to break free. Now, these energetic particles, if they are on this, if they are at the surface, the top surface layer, because even if this particle has more energy, this will bounce with all these other particles. The ones at the surface have the chance to break free from the surface and go to the gaseous state. Okay, so these energetic particles, some of these might be highly energetic and might cross a barrier that can allow them to move into the vapor phase. So there will be some particles which will be moving from the liquid state to the gaseous state, to the vapor state, right? So there will be some moving here. What's the other thing that we have to understand? That there is this gas phase, so this vapor phase. Now, there can be some atoms in the vapor phase too, which have lesser energy and they want to go into the liquid state. So there will be other particles less in energy who want to come inside this liquid phase. So there is this competition between the liquids, between the particles in here and the particles in here. Now the balance, when there is a balance, when the outflow, the inflow is the same, the pressure at that point in which there is no net exchange between the particles going out and the particles coming in, the pressure exerted by the vapor at that particular point is called vapor pressure, right? And vapor pressure is also defined at a particular temperature. Like if you increase the temperature from 50 degrees to 70 degrees, there'll be more particles who will try to leave. Why? Because when you have higher temperatures, it will shift the general population towards this, to higher thresholds. The higher number of molecules will be able to cross that threshold, right? So if you move from 50 to 75, there will be more particles that have energy that can cross that barrier. So that will increase the vapor pressure. You increase the temperature, you increase the pressure. So if you want to define vapor pressure, you have to define vapor pressure at equilibrium when the net of this leaving and coming back is constant, and that has to be defined for a particular temperature. Now, there will be continuous evaporation condensation, but the net will be constant, right? So there's a continuous evaporation and condensation, but the net the net is zero, like that is the equilibrium state. Now, there will be some fluids who want to leave the particles that they do not have stronger attraction forces. They'll be leaving the liquid faster than the others. For example, gasoline have really less intermolecular forces, and that's why it will be leaving the gas phase, that it will be leaving the liquid phase and will be moving to the vapor phase higher than as compared to water. And that's what is called volatility. Like more volatile compounds, they do not want to stay in the liquid state, they want to go into the vapor phase. Volatile compounds do that, right? Now, when you have more volatile compounds, the pressure in here will be more. Now, say for example, what will happen when you increase the temperature? When you increase the temperature, the vapor pressure increases because there will be more particles moving into this vapor phase. Now, when you increase the vapor pressure, what happens? Do you think more particles will be moving to the vapor phase or less? It will be less, right? Because when you increase the vapor pressure, the pressure that this vapor phase is exerting on the liquid is more. It's hindering the transfer of particles from the surface to the vapor phase, right? So when you increase the vapor pressure, it will become harder to evaporate, right? And then it will continuously become harder and harder, and then it will establish an equilibrium. So if you start from nothing in the vapor phase, like in here, if I suddenly close the system, let's assume we have the system, and I suddenly close the system, the vapor pressure, let's assume that there is no vapor pressure in here. If I suddenly close the system, the vapor pressure starts to build up. It starts to build up. And at a certain point, it becomes harder and harder to evaporate if you close the system. Now, if you don't close the system, it becomes easy. Why? Because you're not able to collect this vapor pressure in here, right? You have the vapor pressure, but it's not getting collected. It is blown by because it's an open system, right? Now, talking about an open system, now let's imagine what happens at a different scenario. Like, for example, like if this system is like open, right? So you have liquid water, you have, based on the temperature, say for example, it's in the 25 degrees at room temperature, so it's moving, particles are moving from the liquid state to here, but that movement is extremely less, right? Because it's not so much volatile, so there's not much accumulation of these vapor particles. And there is an atmospheric pressure that is acting on this. So there's an atmospheric pressure that's acting on this, and it kind of forms an umbrella, a canopy on that. And it kinds of, because this pressure is so high, these particles that are here are not able to move out of this closed, like invisible canopy because of the higher pressure. Now, how do you increase the vapor pressure in here? You increase the temperature. Now, for example, you have 20 degrees and you increase the temperature to 50 degrees. So you have more particles in here, more vapor phase particles in here, okay? You increase it to further, say to 100 degrees. What will happen? It will increase it even further. At some point, the pressure in here will be so high that it will match the pressure of the atmosphere. At that point, the atmospheric pressure will not be able to contain this vapor in this invisible lid because it's the same. So, atmospheric pressure and vapor pressure becomes equal at some point when you keep on increasing the temperature, right? So, if you keep on increasing the temperature, more vapor accumulate here. In the beginning, it was less than the atmospheric pressure. Then it catches up and it becomes equal to the atmospheric pressure. So when vapor pressure becomes equal to the atmospheric pressure, the liquid boils off, right? So that point is called boiling.